Find an explicit formula for the sequence of exercise 39 in section 5.6. Now, here's the recursive definition that you would get from exercise 39 from section 5.6. Now, the first thing I should mention is that this is a second order linear homogeneous recurrence relation with constant coefficients because it's in this specific format here, where in this case a equals 1 and b equals 1 as well. And so next we need to find the roots of our characteristic equation here. So this characteristic equation would be t squared minus t minus 1 equals 0. Now there's no easy way to factor this, so we're going to have to use the quadratic equation, which says the solutions are t equals negative b, which is 1, plus or minus the square root of b squared, which is 1, minus 4ac, which is 4 times negative 1, all over 2a. And this simplifies to 1 plus or minus root 5 all over 2. And so we have two distinct roots to this characteristic equation. Now, according to theorem 5.8.3, which is the distinct roots theorem, if we have distinct roots to this type of recurrence relation, then our solution is going to be of this form. So that means our solution will be c sub n equals some constant coefficient c times the first root r, which is 1 minus root 5 over 2, all to the nth power, and then plus some other constant coefficient d times 1 plus root 5, this is the other root, over 2 to the nth power. And it doesn't matter which root you use where here. What matters is that you know how to solve for c and d. Now, we're given initial conditions at the top here, that c sub 1 equals 1 and c sub 2 equals 2. So if we plug in n equals 1 here, we should get 1. So let's do that. This says 1 equals c times 1 minus root 5 over 2 to the 1th power, which I won't do anything there, plus d times 1 plus root 5 over 2, and then to the 1th power, which I'll just leave it alone. That's if we plug in n equals 1. Now let's plug in n equals 2. If we plug in n equals 2, we get 2 as the result. So 2 equals c times 1 minus root 5 over 2 squared plus d times 1 plus root 5 over 2 squared. And so we have two equations with two unknowns. And this is going to be pretty tricky to solve. The way I think that we should solve this is we should take the first equation and rewrite it by multiplying both sides of the equation by 1 minus root 5 over 2. We can also pick 1 plus root 5 over 2, but I'll just pick 1 minus root 5 over 2 on both sides. So the left-hand side will be 1 minus root 5 over 2. But the right-hand side will now be c times 1 minus root 5 over 2 squared plus d times 1/4 minus 5/4. The next thing we're going to do is we're going to subtract these two equations by taking the first equation and subtracting the second equation. So the left-hand side is going to be 2 minus 1 minus root 5 over 2. And then these two will just cancel because they're the same. And then 1/4 minus 5/4 is just negative 1. So we can just fix that to be a minus symbol. And subtracting a negative is really a positive. So this equals d times 1 plus root 5 over 2 squared and then plus d. Now we can simplify the left-hand side as 4 over 2 minus 1 minus root 5 over 2 equals d times, now we can square this and factor out a d. So if we square this, we would end up getting 1 plus 2 root 5 plus 5 over 4, and then plus 1. The left-hand side becomes 4 minus 1, which is 3, and then minus negative root 5 is plus root 5 over 2 equals d times, now 1 is the same thing as 4/4, so 4 plus 5 plus 1 is 10 plus 2 root 5 over 4. But this simplifies, this can be reduced by canceling a factor of 2 in both the numerator and denominator. And so this 10 becomes a 5, this 2 becomes a 1, and this 4 becomes a 2. So this is 5 plus root 5 over 2. And then we can multiply both sides by the reciprocal, which is 2 over 5 plus root 5. So d equals 3 plus root 5 over 2 times 2 over 5 plus root 5. The 2's cancel, and so this is 3 plus root 5 over 5 plus root 5. But then we can simplify this by multiplying the numerator and denominator by the conjugate of the denominator. That'll rationalize the denominator here. And this simplifies to d equals 15 plus 2 root 5 minus 5 over 25 minus 5, which simplifies to 10 plus 2 root 5 over 20. And that simplifies to 5 plus root 5 over 10. So that is the solution for D. Now let's solve for C. So we can go to any one of our equations, and I'm going to take the easiest one here and substitute our solution for D. So we're going to take this equation 1 equals C times 1 minus root 5 over 2 plus D times 1 plus 5 root 2, and we're going to substitute our solution here. And then we just have to solve for C. Now we can multiply both sides by 20. That'll get rid of all these denominators. This will be 10C times 1 minus root 5. And then plus, we can FOIL the numerator here to get 5 plus 6 root 5 plus 5 again. And so this is 20 equals 10C times 1 minus root 5 plus 10 plus 6 root 5. We could subtract both sides by 10, and we could subtract both sides by 6 root 5 to get that 10 minus 6 root 5 equals 10C times 1 minus root 5. We could divide both sides by 10 times 1 minus root 5, and that way we get C equals 10 minus 6 root 5 over 10 minus 10 root 5. We can reduce everything down by 2, so this is 5 minus 3 root 5 over 5 minus 5 root 5. And then we can rationalize the denominator by multiplying the numerator and the denominator by 5 plus 5 root 5. And this simplifies to C equals plus 10 root 5 minus 15 times 5, which is 75, all over 25 minus 125. So that simplifies to minus 50 plus 10 root 5 over 100. So C equals negative 5 plus root 5 over 10. And that's our solution for C. So now we have our solution for D and our solution for C. So now we can plug in our solution for C and D into the original equation, which I'll do on the right here. So C is negative 5 plus root 5 over 10, and then times this 1 minus root 5 over 2 to the nth power. And then we have to add D. D was positive 5 plus root 5 over 10, and then times 1 plus root 5 over 2 all to the nth power. And that is the explicit formula for this sequence. That was a pretty difficult problem, and as you could tell, the recurrence relation is the same recurrence relation as the Fibonacci sequence, and if you've seen the explicit formula for the Fibonacci sequence, then I think you can understand why this explicit formula is a little crazy. Thanks, everyone, and I'll see you in the next video.